Okay, example 8. Here is a little bit of a different problem than what we've had so far. This is the first time that you're going to see that you have things that you're mixing. In this problem, we're mixing two different samples of water. So imagine for a moment I have a graduate cylinder full of 30 milliliters of water and a graduate cylinder full of 50 milliliters of water, or because of the density of water, 30 grams and 50 grams. So I take those, I have my 30 gram sample of water that's at 280 Kelvin, and in my second graduate cylinder I have my 50 grams of water that's at 330 degrees Kelvin. I mix them together and eventually their final temperature will become the same. Okay, so let's talk about how we tackle a problem that is a mixture of items. The problem asks us to find final temperature. So once again, if this was mixed up on a mastery quiz or test, we know we need to have T's. So we know to use this one. Okay, lots of stuff on here, but for now, focus with me for just a moment. Then I'll pause the video and get some time. So we know that we have a 30 gram sample of water at 280 Kelvin, and it's mixed with a 50 gram sample of water at 330 degrees Kelvin. So what we will do then is we will set our Q's for each equal to each other. Because ideally the thing that's warmer is going to transfer heat to the thing that is cooler, or the thing that is cooler will absorb heat from the warmer item. So we set Q for water at 30 degrees equal to the negative Q of water at 50 degrees. Now why is this negative? Well, we make this side negative, or we make the Q quantity negative that has the higher temperature, because it's going to release, hence the negative symbol, heat from at 50 degrees to the one that's cooler at 30 degrees. So then for each we will figure out MC delta T, remember that's what Q stands for, so M times C times delta T equals M times C times delta T for this side, but we're going to make it negative. So before we plug anything in, we're going to do our same thing that we've always done. We're going to make our list of variables. So here I've made my list of variables. M is 30 degrees Celsius. Excuse me, let me try that again. M is 30.0 grams. Okay, got that from my 30 gram sample. I know the specific heat of water, because remember both of these are water. We have memorized that from our blue card, or we'll use it, I should say, from our blue card. 4.18 joules per gram degree Celsius. We are looking for final temperature, so we do not know it, but we do know that it starts at 280 degrees Kelvin. No, we can't use Kelvin though, so we got to convert. And if you recall from first year chemistry, degrees Celsius equal to K minus 273.16. Now this might be blue card worthy, so you might think about writing that down later on your blue card. So I take 280.0, and I believe I've taken the liberty of adding a 0.0 to that just for sig fig purposes. Yes, I did. Minus 273.16 degrees Kelvin, which is 6.8 degrees Celsius. I'm sorry, 280.0 Kelvin minus 273.16 degrees Celsius equals 6.8 degrees Celsius. Okay, I did the same thing. I'm not going to go down, I'm going to go over so I can show you that on this side, where I have 50 grams of water, I did M, 50 grams, C, it's water, so it's 4.18 joules per gram degree Celsius. Final temperature, we don't know, that's what we're solving for. But we do know the initial temperature of the 50 gram sample is 330 Kelvin. So we know we got to convert it. Degrees Celsius equals K minus 273.16, so 330.0 Kelvin minus 273.16 degrees Celsius equals 56.8 degrees Celsius according to sig fig rules. Alright, so now that we have all our variables, we're going to go down. At 30 degrees Celsius, we know it's M times C times delta T equals negative M times C times delta T. Remember, this is Q equals Q, or Q equals negative Q. Why is this side negative? Recall again, this side is negative because it's at a higher temperature. So then I plug in my values from up above, 30 grams, 4.8 joules per gram degree Celsius, times, now remember what delta T is, TF minus TI. So there's my TI, my TF is unknown. On this side, I set it equal to negative 50 grams times 4.18 joules per gram degree Celsius times the quantity TF, which we don't know, minus the temperature 56.8 degrees Celsius. Now, the math is a little bit more complex here. I will need to do that nasty word of distribution to be able to solve this. So I'm going to distribute this through both. And when I distribute this through, I get this piece. And when I distribute that, I get this piece. So 125.4 joules degrees Celsius TF minus 850 joules. Notice that degrees Celsius will cancel. When I multiply this times this, degrees Celsius would cancel here. On the other side, don't forget your negative symbol. Negative, I'm going to distribute that through those two pieces again. 209 joules degrees Celsius TF plus, now, the answer in my calculator is 11871.2 degrees Celsius. But, because of sig fig rules, I'm multiplying, I can only have 3 sig figs, so then I went ahead and just rounded it to 1.18. let me try that again, to 11900 joules. Alright. Now, what am I going to do next? Well, what I'm going to do next, I'm going to combine like terms. So, I'm going to get the TFs together on one side over here, and then I put the joules, the non-TFs, on the other side. So I added 201 to both sides and got this, 334 joules degrees Celsius TF. So I put my TFs on my left, and my non-TFs on my right. So I added 850, got this, and then I could divide, not multiply, I can divide both sides by 334 joules degrees Celsius. Joules cancels, leaving me 38.17 degrees Celsius.